Hello, my name is Kristen Merritt, Project Manager at ELSA's Flight, and I want to welcome you to the Project Talk on Introducing Biomedical Researchers to High Performance Computing, teaching QIIME2 on the Nucleus HPC Cluster Environment. This project is part of the Engagement, Training, and Sustainability Work Package of the CompBioMed Center of Excellence. Bringing this project and this talk to life was truly a collaborative event, so before we begin, we would like to thank CompBioMed partners at UCL, the University of Sheffield, associate partners ELSA's Flight, and to our student authors from the University of Sheffield Medical School for making both this project and this presentation a success. We'd also like to thank those who funded this project, the European Commission for Horizon 2020 for the CompBioMed Center of Excellence, and the ELSA's Flight HPC Community Outreach Fund for the compute resource management utilized throughout the project itself. Here's a brief look at the agenda of our talk, which features speakers from all aspects of the work we did on introducing HPC to new biomedical researchers from June to November 2020. But before we can talk about our project work on the QIIME2 application and the unfederated cluster environment the students worked in, let's learn a little bit more about CompBioMed itself. Here's Dr. Andrea Townsend-Nicholson of UCL and Dr. Andrew Narracott of the University of Sheffield.
CompBioMed is a European Commission Horizon 2020 funded Centre of Excellence focused on the use and development of computational methods for biomedical applications. Although computer-based modeling and simulation is well established in the physical sciences and engineering, computational methods are only now reaching maturity in the biomedical domain, with predictive models of health and disease increasingly becoming relevant to clinical practice. A key and futuristic objective of the consortium of researchers in CompBioMed has been to integrate computational methods, biomedical data, and increasingly powerful supercomputers in order to build a virtual human, an in silico twin of an individual. Engaging clinicians is an important part of building the virtual human, and we chose to start this process with medical students.
The course material was delivered as part of a student-selected component within the undergraduate medical degree at the University of Sheffield, building on previous experience of delivery to medical students at UCL. The Sheffield SSC is a full-time 6-week research attachment at the start of their second year of study. Students have free choice of topic, and the SSC ran at full capacity of 20, demonstrating the enthusiasm for this area of research.
We think of ourselves as human, but we have at least as many bacterial cells in our body as we have human cells. Not all bacteria are bad for us. As we learn more about these microbial passengers, our microbiome, we are beginning to understand how they influence our health and disease. Our goal for our medical students was for them to use high-performance computing to explore the relationship between a human microbiome and human health. QIIME stands for Quantitative Insights into Microbial Ecology. We used the QIIME2 platform to understand the diversity of microbes from experimentally obtained samples of human microbiomes. We analyzed these DNA sequences to explore the relationship between a microbiome and a disease state. To achieve our goals, students needed to learn how to use the command line, basic Linux, how to run the QIIME2 computational pipeline on HPC, and how to visualize the output obtained from a computational system lacking a graphical user interface, which was something completely foreign to them. We conducted an entry and exit survey. The entry survey allowed us to tune our teaching delivery to suit our cohort of students. The exit survey allowed them to see how far they had come in their understanding of microbiomes and the development of their confidence and competence in using HPC resources.
To ensure strong student engagement, a contact session was delivered every day using a broad range of mechanisms. Between planning and course delivery, some aspects were adapted as a result of COVID-19. Overall, this had relatively little impact and may have enhanced some content due to the strong focus on preparing online resources in advance. Course materials made available using the Blackboard virtual learning environment. This included lecture notes, web resources, reference documents, and video recordings of previous sessions. Session types included traditional lectures, drop-in sessions, and workshops. Drop-ins allowed students to raise queries and develop computational skills. Weekly, long-form workshops focused on the use of the Cloud HPC instance, with step-by-step guides to describe navigating the resource, transferring data to their local machines, and running the analyses. Sessions were delivered using Blackboard Collaborate, allowing interactive polls. These were very useful in tracking understanding of topics and progress with the compute tasks. The group chat was used to troubleshoot issues and ensure the students played an active role in the session. Where necessary, direct video calls to individual students were used to troubleshoot technical issues, allowing individual screen sharing. However, this was not generally required and was mostly associated with initial setup to provide command line access to the cloud compute resource.
Cloud instances can be configured to be very similar to the traditional HPC environment, but can be scaled up or down to meet demand. We maintained a baseline instance, Nucleolus, throughout the course, but expanded this into a larger instance, Nucleus, for workshops. This approach reduced the need to ring-fence allocation, but provided a real-world experience of using HPC resource. It minimized queuing during teaching sessions, while exposing students to normal queuing practices outside of planned teaching delivery. Use of the cloud was familiar and appealed to students. It helped to compensate for obliging them to use the command line and allowed us to introduce them to modern compute technologies.
Thanks, Andrea and Andrew. Now, let's get a closer look at the Nucleus Cloud HPC cluster environment. To tell you more, here is Stu Franks of Alsace Flight and Art Hottie of UCL.
My name is Stu Franks, a technical product manager for Alsace Flight Limited. What is probably interesting to most of those attending is that Nucleus itself is a completely cloud-driven HPC environment. This means it isn't federated to an on-premise site, and for CompBioMed, this is a good thing. Nucleus exists as its own HPC cloud environment, or cloud cluster, which currently resides on AWS. It's built and managed through Alsace Flight Center, which holds the documentation, materials, templates, and desired architecture that each training should hold. To keep things cost effective, Nucleus lives in a small state when not being actively used by students or researchers. It consists of the core infrastructure and a single small compute instance, until high utilization, at which point the cluster will grow to support the workload, returning to its smaller state upon job completion. Storage is also quite minimal. Right now, it is only hosting the workloads needed for its upcoming training and nothing else. All non-critical material has either been stored on Alsace Flight Center or, in the case of the student research projects, having moved onto their home cluster once their training is completed. Because CompBioMed has a global reach and utilizes partner sites for on-premises work, you cannot have a training setup that just works on one cluster. The amount of setup and configuration time required to be able to deliver training work in applications such as QIIME2 would require far too much in resources. So, rather than having to go through and repeat the setup process on site or on the platform the institution utilizes, the CompBioMed team are doing it just once, and doing it on cloud. Cost is another factor that matters when running project-driven, flexible workloads. The prices of dedicated hardware for bursts of utilization is far less affordable than scaling up a cloud system when the resources are required. This allows budget-conscious implementation of HPC solutions. With the migration to new tools and constraints of turning around jobs quickly during times of burst resource usage, rapid testing and evaluation of the system is needed. The flexibility of the cloud allows for various resource configurations to be added to the cluster, for testing various job configurations and turnaround times. The CompBioMed team utilizes Alsace Flight Center as a centralized knowledge and support repository. Here, they can collaborate with Alsace to solidify their cloud workflow that can be utilized on their cloud clusters. I'll now hand you over to Art, who will talk you through the QIIME2 application usage, testing, and optimization.
Thank you, Stu. My name is Art Hottie, I'm a 4th year MSci biochemistry student at UCL. Before initiating the workshop at Sheffield, it was crucial that we understood the nature of QIIME2 and its performance on HPC clusters of varying configurations. Specifically of interest was how the wall time of the analysis pipeline varied as a function of the compute power of the instance. Our aim was simple: to derive a cost-effective, minimum viable cluster which could accommodate for the needs and time constraints of the workshop. The QIIME2 package is an open-source bioinformatics platform for the analysis of metagenomic data. In short, it takes experimentally determined sequences derived from microbial communities and via a series of algorithms termed plugins, processes and analyzes them to give insight into microbial communities and their structures. From a software perspective, QIIME2 is somewhat modular in nature, consisting of an array of plugins, each with their own functionalities. These can be arranged to produce various analysis workflows that are suited to the needs of the researcher. Here, we see a typical QIIME2 workflow, specifically the one used for the workshop that we're currently running at the University of Sheffield. There are 4 stages, each with potential for parallelization: data import and filtering, taxonomic classification, phylogenetic analysis, and alpha and beta diversity analysis. As input data for testing, sequences obtained from experiments previously conducted at UCL were used. The use of multiple variant sets of data ensured that the cluster would perform robustly across datasets. Before initiating testing, we set a clear goal for the optimization of the system. For this workflow to be viable in a workshop setting, it would have to run from start to finish in the space of less than 1 hour for each dataset. For our baseline system, we selected the AWS T3 Medium instance. This is optimized for burstable workloads and contains 2 vCPU cores and 4 GB of memory. With this instance, the wall time of the pipeline varied from 92 minutes to 132 minutes depending on the input data. Considering our 60-minute goal, an upgrade was clearly needed. For the subsequent instances, we therefore decided to switch to the AWS C5 range, which offers instances that are optimized for compute-intensive applications. Our first C5 instance was the C5 Large. With this system, we observed speed up to a range of 72 to 107 minutes depending on the input data. However, this was not sufficient, so we upgraded, once again, to the C5 X Large instance, and observed a range of 52 to 73 minutes for the overall workflow wall time. Following this, testing and optimization was conducted on the C5 2X Large instance. At this step, we achieved the 60-minute wall time threshold that we were aiming for, obtaining a range of 42 to 56 minutes of wall time for the whole pipeline. To optimize this 2X Large system, we analyzed the scaling of the deblur plugin, the longest step within the pipeline. Interestingly, the deblur plugin contains a parameter which allows the user to tune the number of threads over which the computation of the algorithm is parallelized. The aim was to check whether 8 cores was indeed optimal at this step for each set of data. Furthermore, we also wanted to deduce whether the process was CPU or memory bound, as between each instance, both the number of vCPU cores and amount of memory were increasing. Upon real-time analysis of the deblur algorithm running at 8 cores and 16 GB of memory, continuous CPU saturation was observed, with negligible memory dependence on the order of 20 kilobytes. After running multiple 8-core tests using between 2 GB and 16 GB of memory, it was conclusive that the wall time of the process is completely CPU bound within this range. This allowed us to conclude that with each instance upgrade, the speed up of this rate limiting step was due to an increase in the number of cores rather than an increase in the amount of memory available in the system. In turn, to gain further insight, the parallelization parameter was tuned in order to derive the wall time of the algorithm as a function of the number of cores over which it is parallelized. From this data, it became clear that for experiments 1 to 3, the performance of the algorithm was as expected, with the lowest wall time being achieved at 8 cores. An interesting finding, however, was that for experiment 4, there was a decrease in speed between 4 and 8 cores. To test this anomaly, we ran 3 additional repeats at both core counts and found that the trend persisted, with minimal variance in wall times between the repeats. The cause of this is currently a subject of further investigation. Regardless of the cause, however, the conclusion was 1, that 4 cores are optimal at the deblur step for this specific dataset, and 2, on a more general level, that depending on the input data, algorithms may scale in non-trivial and variant ways. In summary, therefore, we tested different AWS configurations and determined that the C5 2x large instance was optimal for our workshop setting, achieving sub 60-minute wall times for each dataset. With this configuration, we also determined the optimal parameters for each dataset at the rate limiting step. This is the configuration that we are now using as the basis of our production instance.
Let's look at some of our initial findings from working on this project. Summing things up took a bit of thinking, mostly because people will be concerned about cost, specifically around the cloud platform. What needs to be stressed, however, is that there are 4 elements that went into the design and launch of this educational project. These are the cloud platform and core infrastructure through ELSA's Flight Center to maintain the nucleus environment, project and analysis time from ELSA's flight, project teaching and analysis time from UCL, sponsorship, teaching, and analysis time from Sheffield. Let's see how these elements play out over a timeline. It's important to take note that due to the requirements of SC20, the data is valid up to October 9th of 2020, with estimations taken into consideration through October 31st, which is the end of the project. The key at the bottom of this graph shows each of the groups involved. Please note that ELSA's flight also includes maintaining a persistent nucleus cluster and all the maintenance involved. Cloud costs were broken out specifically to show how they impact overall budget. This project launched on June 17th of the year and had a fairly long setup phase. This is because we needed to take into account shifting start times for the course, assembling the project team, and locating all the data and information which was spread across 2 systems. Once the team assembled, the noisiest part of the project took place. This is where the team tested the appropriate instance sizes, uploaded and amended data and scripts, and brought together the course materials. Once testing was completed, the University of Sheffield was onboarded into the system, and preparation work was underway to ensure that the coursework would meet objectives. As the noise of testing had completed, the nucleus test cluster stayed in a minimum viable or MVC state, ready for use. 2 spikes in both person hours and compute usage came next, as the planned workshop required nucleus to scale to 10 times its MVC state. Because this is the first time delivering a workshop, monitoring the in-cluster environment was much higher than normal. The second workshop held a similar focus, with a scale down happening in both the compute and project management as the rest of the course played out. As of this recording, it is anticipated that nucleus will not need to be scaled again, as the processing time of student projects does not need to be compressed into a class workshop, thereby dropping the cost of compute. Once the course completes, the analysis phase begins, where the teams work together to package lessons learned and plan for the future. Student data is offloaded, and the nucleus returns into a test state in order to reduce both overhead on compute and time cost. Each phase of the project has its own considerations to take into account, not only the compute and storage needs, but also the needs of the team. And while the initial investment was high, future time and cost spent on the project should reduce. Areas where less time should be spent would be in the requirements and testing stages, as well as less person time spent on monitoring, but with the knowledge that an onboarding spike should be anticipated. It's also important to note some caveats. Compute instance types may need to be significantly altered, The project team may change, or QIIME2 might be replaced with QIIME3 and require more testing and analysis time. After all of this, it's still likely that you'd want to have a better understanding of actual costs. I want to stress that when pursuing projects like these, you should also consider the time and effort expended outside of the project, and not just the cloud time. Our costs focused on courses launched around a persistent cluster environment, primarily the use of the ALSYS flight team, ALSYS Flight Center, and the cloud cycles used on the course. Overall, the time spent on this project was approximately 4 months, and there was a total cost of £6,500. It should be estimated that replication costs should decrease by about 40% in person time, and move more towards a change request style of management, so long as none of the caveats come into play. So there you have a look at our initial findings. Thank you for listening to our presentation. If you'd like to learn more about the CompBioMed Center of Excellence, the core partners UCL, the University of Sheffield, or associate partners ALSYS Flight, links to each group can be found on the screen.